Here on Chalk Talk, we've been discussing FPGAs for many years. And many of you probably know that FPGA based prototyping is an essential tool in the verification of many SoC and digital designs. And in recent years, there has been a bigger and bigger need for prototyping. But prototyping has been in the design and verification arena for a super long time. So, what is driving the growth for FPGA based prototyping? I'm glad you asked, my friends, because that's exactly what we're talking about today. Hi, I'm Amelia Dalton, host of Chalk Talk. In this episode of Chalk Talk, Levia from Siemens and I explore the trends pushing a need for hardware-assisted verification, how modularity can speed up system design, and the benefits that the Veloce proFPGA CS platform can bring to your next design. And before we get started, don't forget to click that link. There you can find even more information about this topic from Siemens.
Hi, Oz. Thank you so much for joining me.
Thank you, Amelia. I'm really happy to be here. Your observations are correct. Prototyping is definitely not new, but you're right in noting that in the recent years, there has been significant growth in the demand for prototyping and also in the use of prototyping. There are many drivers, but the main drivers are two business trends. One is the fast growing market for AI and machine learning. And the other one is the emergence of the hyperscaler class. Hyperscalers are companies that typically you would think of as system houses, but now they make their own silicon. They make their own chips, and a lot of those chips, AI, memory, processors, and so on. What is common to both of those factors is the increase in the software content on these target chips. The larger software workload content requires prototyping because other methodologies are just too slow, and typically silicon is available a lot later. The silicon payload growth is very rapid, and the verification effort of the software is growing in an exponential rate. And FPGA prototyping then is essential, indispensable for the early pre-silicon software verification.
Oz, that makes sense. So I understand that in the recent past, with the introduction of the BP1902 FPGA from AMD, there seems to be a shift in the landscape of FPGA prototyping. With new capabilities and added complexity, the newest FPGA is creating new opportunities for users and vendors.
The new VP1902 device is very different. Now, it should be said that the programmable fabric is not that different, how the programmable logic is implemented. But there are several changes that make this device a lot more useful for prototyping, but at the same time, also more complex and more challenging to use and implement. I think some of them, one is it's a much larger device. So larger gate capacity is very useful because you can fit larger designs on the chip and have much less need for partitioning. There's also an opportunity for increased performance because partitioning typically reduces the performance. The additional I/O bandwidth, coupled with the introduction of hard IP for some of the important protocol, reduces the need to implement some of those functions in the programmable logic. The cost per gate, not the cost, but the cost per gate is lower, which makes for a more affordable system for the user. And then finally, I would mention that because there is a lot of embedded memory on the device, it allows for modeling a lot more of the design memories right on the chip as opposed to in modeling or using the programmable logic. Now, at the same time, the device is expensive. There's a lot of pins, almost 6,000 pins. The power architecture is complex. The clocking architecture is complex. And this is specifically difficult and risky for users that are attempting to create their own prototyping system or their own prototyping boards.
So, Oz, I understand that Siemens was the first to market with a production prototyping system based on the VP1902 FPGA. Is that correct?
Yes, Siemens was the first to market with production VP1902 based devices. The lead time that we had was about 6 months, and our team used the time to optimize the performance of the system. One of the ways that we were able to do that is through very close and frequent discussion and collaboration with AMD, where our R&D team were able to gain insight into the VP1902 and make early technology choices. But again, going back to the benefit to the user, really being first to market and having such a long lead time means for the prospective users that by now our system has had many flight hours, a lot of types of designs, a lot of verticals, and many types of users.
So, Oz, what about your product architecture enabled you to get to market first? Are there any specific aspects of your system that were useful?
Yeah, and I can mention maybe a few of them. Our R&D design choice was to focus on scalability and modularity. Having a modular design saves a lot of time since key components can be reused. Specifically, in our system, a single FPGA module is used across all of the form factors of proFPGA CS. We also elected to provide a full access to the I/O pins of the device, and the architecture is a very powerful feature for users and allows us to create a much simpler and faster design.
Oz, how is this module used in the system? You mentioned reuse and multiple form factors, so can you talk a bit more about that?
Yeah, so in addition to modularity, our R&D designed proFPGA CS for scalability. So creating scalable form factors greatly accelerated the design process for proFPGA CS, and it allowed us to come to market more rapidly. Now, in addition to that, it's not just an internal benefit, but in addition to that, it has a lot of added value to users. Specifically, the ability to add just the capacity that is needed and no more. But at the same time, be assured that there is really no practical limit to how much capacity you can add. That is what scalability means to us. For the users, it's about cost efficiency and future proofing.
Fantastic. All right. So, Oz, can you give us an example?
Yeah, the basic unit is an FPGA, the module with one VP1902. ProFPGA CS offers multiple form factors, and each of them can be populated with as few as one FPGA module and as many as can fit into the specific form factor. And additional capacity then is very easy and very cost effective. The first one is the UNO. The UNO is a single FPGA desktop designed for individual use. It can be a network resource, but it's designed for an individual use and very high speed. Two other desktop configuration. One is the quad and the other one is the hexa desktop. They can be populated with as many as one or two, three or four or six FPGAs respectively. And then another form factor is the hexablade. The hexablade is a data center architecture standard, and it's actually designed to go into a rack, even though it can also be used as an individual module. And then finally, the last configuration is the multi-blade tower system that is populated by as many as 10 hexablades and can support between 1 and 60 FPGAs. One important benefit to the users, in addition to having early access to the new FPGA, is that our system is very affordable to own and to scale. For our users, this translates into a financial advantage because you only buy what you need. Also, versatility of use mode and portability. We call this entire product family Veloce Pro FPGA CS. Now, this scalability is useful not only in the initial stages of engagement, but also a time of broad deployment because the different form factors can accommodate different needs, different locations, different teams, and different use modes.
So, Oz, that last configuration is really interesting. If I was a user, I would want to also make sure that I can not only add one FPGA at a time, but also access individual FPGAs so I can service multiple users on a larger or any configuration.
Yeah, I think you're reading people's minds. That's exactly true. Fine-grained or FPGA level access is very important especially when you consider a very large configuration. It's important, of course, to run very large designs using multiple FPGAs, but it's also critical to allow a company or a user or an organization to use the same physical system, large FPGA installation, to allow multiple users to access smaller designs individually on the same platform, but with complete autonomy and privacy. In proFPGA, the granularity that we allow is a single FPGA. And one place that has made it publicly that they're using this capability is ARM in the UK and in Texas. They have a very large scale installation of proFPGA CS, hundreds of FPGA, and granularity for them is about utilization, flexibility, and also reuse of the same configuration for multiple purposes.
This is really interesting, Oz. Also, isn't it true that compiling the RTL design to an FPGA based prototyping is really hard and time consuming?
Traditionally, yes. In a typical FPGA prototyping system, can take a very long time to map the design RTL or the RTL that is designed to go into the synthesis and into the ASIC to FPGAs. This is because the RTL that is created for design implementation traditionally requires some help before it can be mapped into the FPGA. And in the case that you are mapping the design into multiple FPGAs, so does the partitioning of the design. It's even more true for customers or users that are attempting to create their own prototyping systems. Partitioning and compile to FPGA is a difficult task. One of the advantages of proFPGA CS is that we require no modification to the RTL before it's synthesized. Mapping to one FPGA is one thing, but the design, if it's a larger design, must be partitioned among multiple FPGA. And without automation, as I alluded, this is a really, really hard and error-prone task. proFPGA CS, what the users get is a complete automation of the partitioning. It's not just automation, but it's also the assurance that the partitioning is not just efficient, but also predictable. Predictable meaning that if I mapped a portion of my RTL to a particular FPGA, I can be assured that it's going to go through the entire process all the way to place and route and timing, and it's going to do so optimally. Prototyping is, of course, also about verification, and verification means debugging. In that respect, it's very important to highlight the capabilities of being able to insert probes and being able to siphon data out of the design at runtime. Once the design is partitioned, there's also additional tasks that are required to prepare the design for the place and route, clocking, pin muxing, and so forth. Here, the software again can do all that work automatically and get the design ready for the Vivado place and route task.
So, Oz, users that I speak to consistently mention debug as a weak point for prototyping systems. Specifically, users of emulation voice this concern.
Yeah, this is a legitimate concern. As we just discussed, prototyping is not just to run fast, it's about verification. In this regard, debug is an important consideration and a critical capability. Now, while we're running prototyping at software speed, it is also important to have different levels of debug support that each can offer different capabilities with respect to hardware debugging. And in proFPGA, yes, we offer three levels of hardware debugging. The first one I sort of alluded to very quickly. It's called probed debugging. At compile time, the user can specify a bunch of signals to be probed. The advantage of that methodology is number one, the signals retain their RTL name, and number two, and maybe not less important, all of that tracing can be done at full speed. There is no impact of the runtime performance of the prototyping system. The second approach is a runtime approach, and it's called probeless debugging. This is a full state capture. Lower speed, using readback from the design, it's possible to reconstruct all of the combinatorial logic in an offload process. The third approach is even more surgical, and it allows the user to break the execution of the prototyping system and step through the design in a single clock instrument. That is, the ultimate visibility and the ultimate control, but obviously it's done at human speed as opposed to machine speed. That's the scope of hardware debugging.
So, Oz, you said that prototyping is about software verification. How can the user debug the software?
That's a great question. Yeah, obviously, hardware debug is just one aspect. Software debugging requires several capabilities. One is visibility into this design data, meaning signals, variables, memories, register. And then the other one is the ability to extract data from the design at high speed. Another aspect of debugging for software is the ability to force or to rewrite memory data. So, as many software engineers know, one debugging methodology is to try to go into the design and modify some of the values of variables or some of the values of memory and see, whether that has any positive effect over the system.
Oz, what about stimulus? I would assume users would want to connect the prototyping to external sources and interfaces.
Yeah, that's absolutely true. Because prototyping runs at much higher speeds than simulation, obviously, and even emulation, it consumes a lot more data because it runs faster for longer times. And therefore, it needs to be made possible to connect to at speed or near speed interfaces, cards, for common communication protocols and memory protocols, things like very simple essentials like JTAG and UART, networking protocols like PCIe and Ethernet, and of course multimedia like HDMI or USB, USB-C, and so forth. In addition to that, there's a requirement to support other types of interfaces like memories. Not all the memories in the design can be implemented and supported inside the FPGA. Some of them are external by design, but some of them, even if they are inside the ASIC, they cannot be modeled because the FPGA embedded memories do not have the capacity or do not have the capabilities. And therefore, it's important to provide memory cards and memory models. The last capability is virtualization and virtual models. These are software models that can complement the physical devices, and they are typically a little bit slower, but they allow a lot more visibility, control, and maybe even better debugging.
So, Oz, going back to what you said before about modularity and scalability, does that mean that one would be able to take the prototyping system out of the workplace or lab?
Yes. Actually, modularity and scalability of the proFPGA CS enable use in the mobile environments and also use in reference designs. Mobility is basically about the ability to take the prototyping system on the road, out of the lab.
Fantastic. All right. So, can you give us an example?
proFPGA CS is used by autonomous car makers, electric car makers, mobile device manufacturer as a mobile verification and prototyping system. It's possible because the form factor is not that big. The Uno and even the Quad and the Hexa are on a scale that a single individual can lift them and position them inside a chassis or a cart or some other way. The power needs are definitely modest.
Oz, when you say reference design, do you mean that your users can service their users?
Yeah, basically that's what I mean, exactly. Many IC providers obviously have their own software developers, but they have to support external software developers. And the prototyping system can double as a reference design that can be very cost effective. For example, the Uno and the Quad system are a perfect fit. One example, a very interesting example, is RISC-V providers. RISC-V is a standard microprocessor, but it allows the providers to create custom instructions. And if you are a user of these providers, what you would want to know is that these custom instructions actually are going to work well for the software that you are writing. So these RISC-V providers provide a prototyping system with the design already baked in to their users, so they can verify their software prior to the final delivery of the IP.
So I understand the value and flexibility that scalability and granularity can offer, but I assume that with the increased size, the prototyping system must also support remote access.
Yeah, remote access is, well, a must when the organization resources and people are not co-located. But even when the prototyping system is not in the immediate vicinity of a user, if you have a large quantity of prototyping systems that are too big to fit on a desktop, but even desktop system might be necessary to be accessed by multiple users that are not co-located. So remote access is a must, and to service that need, proFPGA CS is essentially a network resource. Just plug a network cable into it and log into it just like any other network device.
So, Oz, before we conclude, what can an experienced prototyping users expect in terms of capacity and performance of the VP1902 based prototyping system?
Every design will be different, but the goal and the reality that we are seeing is always to, obviously, to reach the highest capacity and performance. High capacity saves money, high performance saves time. What the marriage of VPS and the VP1902 FPGA in proFPGA CS and the automatic synthesis and partitioning, what we see is as much as 2x capacity and about twice the performance of previous generation. But as I said, every design will be different. And, I hope this presentation provided value to you. I hope you enjoyed it. If you want to know more, there's a couple of links here for you to use. One is a white paper, Meeting the Challenges of Concurrent RTL and Workload Verification and Validation. And the other one is, of course, you can visit our proFPGA CS page on the Siemens EDA web pages. And I really thank you for your time.
Thank you for your time, Oz. It was a pleasure speaking with you. Before we go, you didn't forget to click that link, did you? There you can find even more information about this topic from Siemens. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, head on over to the Chalk Talk section of EE Journal. You can't miss it, it's right across the top. Or head on over to YouTube, youtube.com/EE Journal.